And so we're back for another flipped lesson. This is from our new unit 2.3 on Newton's law of universal gravitation. And our first flipped lesson has to do with rotational speed, because we're starting off this unit by learning a little bit, getting a little background on circular motion. So some real-world connections that this topic connects to are merry-go-rounds. If you've ever been on a merry-go-round or a carousel, you notice that there's often different rows of horses. There might be a horse on the outside rail and a horse near the inside rail. There's the center of my merry-go-round that it's spinning. So which moves faster, the horse near the outside rail or the horse near the inside rail? A lot of carnival rides involve circular motion, so why don't the riders fall out of those rotating carnival rides that spin around with those riders along the edge? Also, if you have ever run track or seen a track meet, you'll notice that a longer distance track race, rather than having all of the runners start at the same spot along the track, they actually stagger the starting position. So the first runner might start a little forward, the second runner further back, the third runner even further back. So why do they stagger that? Also, by the time we finish this unit, you'll understand what circular motion has to do with why astronauts seem to be weightless in space. Spinning objects such as ice skaters and carnival rides turn around an axis. You've talked about axes before in algebra, but especially in geometry when dealing with shapes. And an axis is just a straight line around which that rotation takes place. So usually a spinning ice skater has an axis that travels straight up and down through her body, and she spins around that axis. A lot of circular carnival rides, like this one, have an axis at the center of the platform that the whole ride turns around. Now, when an object is turning around an axis that is internal, that means the axis is actually somewhere within or passes through the body of that object, we call that a rotation or a spin. So rotation or spin is happening around an internal axis. So we say that the ice skater is rotating, this platform is rotating, or it is spinning. It is spinning around an axis that passes through the object itself. However, if you look at the riders on this carnival ride, they're spinning around an axis that doesn't actually pass through their own bodies. And in that case, we call that a revolution. A revolution happens when you have an external axis around which that object is turning. A very common example that's often used in a lot of physics books since I've been in high school and college is a turntable. So you have to think back, before you were born, before CDs, we used to listen to vinyl albums on a turntable. The turntable is rotating around its axis. It's illustrated in this diagram. So this is the axis of that turntable, and the record itself is spinning around that axis. And physics books love to put ladybugs on turntables. I don't know why, but for some reason it's got to be a ladybug. There it is, right there. That ladybug is sitting at the edge. It's revolving around that same axis because that axis is passing through that turntable and not the ladybug itself. The Earth itself, the planet Earth, let me draw it right here, experiences two types of rotational motion. It is revolving around the sun. So if you picture the sun at the center of our solar system, the planet Earth is revolving around the sun every 365¼ days. At the same time, it is rotating around an axis. That axis passes through the north and the south poles. So the Earth is actually doing this simultaneously. It is rotating around its internal axis, while at the same time it is revolving around the external axis of the sun. now that we're talking about circular motion, there's actually two types of speed that we consider for those objects. So if you think back to that idea of a turntable, or even a more modern CD, that CD is spinning around that internal axis, that little point which that CD is connected to the CD player. So the CD is spinning and rotating around that internal axis. Now, which part of that CD is moving faster? Now, people may answer differently because some might consider what we call the linear speed, while others are going to be considering the rotational speed. The linear speed, that's really the speed we've talked about so far this year. And that is just the distance moved, so how far something has moved, divided by the unit of time. How much time did it take for that distance to be traveled? A point on the outer edge of the CD is going to travel a greater distance around during a single turn than a point towards the inner edge of that CD. So if you think about it, a CD or a record is a circular object. The closer you are to the center, you are actually at a circle with a much smaller radius and therefore a much smaller circumference than if you were standing at a point towards the outer edge. The further away you are from that center, the greater your radius is, and you will actually have a circle, a circular path with a much larger circumference. So if you're at the outside of the track, you would actually have a greater linear speed. Linear speed is often referred to as a tangential speed. The reason why, if you look directly down onto that circle, that circular path, if you are here, at any given moment, the speed, the direction of it, is what we call tangent. That direction is tangent to the circle. So if you think it's just that very small point, there's a line that is traveling right up against the circle. And that word that we use is tangent or tangential. Rotational speed is also known as angular speed. Angular because being a circle, we can actually divide it into 360 degrees worth of angle. So all parts of that CD rotate about their axis in the same amount of time. So this rotation is usually considered the number of rotations per unit of time. So this rotational or angular speed is often expressed in units of RPMs. RPMs just means revolutions per minute. So the meter in your car that tells you the RPMs is letting you know how often some part of the engine is revolving every minute. So the higher the RPM, the faster it's turning, the more it's going to turn every minute. And the angular speed is actually related to the tangential speed. So the relationship between the linear or tangential speed and the rotational, also known as the angular speed, is a pretty basic one. The tangential speed is equal to the rotational or angular speed So that's it for this lesson. However, there is a next step. First of all, I hope that everyone got a copy of the handout so that you can take notes on this lesson. And there are some questions for you to think about what you have learned in this lesson. Also, a little try this at home demonstration. If you can, try to find a can of soup or a can of vegetables will do, that is shaped like a cylinder. That means both the top and the bottom have to have the same radius. And just roll it across the table or roll it across the floor. And then find a tapered cup. Usually, most foam cups, plastic cups, you'll notice that the top rim of the cup actually has a larger radius than the bottom. So we have a large radius versus a smaller radius. And roll that tapered drink cup. And I want you to notice, does that cup roll straight or does it curve? So, and which end of the cup covers more distance as it rolls? So compare both the rotational speeds and the linear speeds of the can versus the tapered drink cup. Now, obviously most of the drawings are my own, as you can tell. However, the other images, I do want to give credit to the Prentice Hall 9th edition of Conceptual Physics. They have some great drawings that I have to admit I did borrow for this demonstration. I'm sorry, but I'm not very good at drawing a turntable with a ladybug on it. Not in the detail that I would like. So I hope you enjoyed this lesson. Please come in with any questions or post a question on Twitter or send me an email.